Hi everyone. So in this video, we're going to be introducing polar coordinates, which are basically just another way of describing points in a plane. So instead of describing points with an x coordinate and a y coordinate, instead we'll be using a different coordinate system called polar coordinates. So we'll talk about, how to actually graph points using polar coordinates, as well as graphing actual curves. So this is a topic that you should have learned about in your pre-calculus class. So if you took Math 142, which is like pre-calc 2 at North, then you definitely should have learned this. So I made a couple of videos in my 142 class last quarter that I'll link in the video description here. I will be basically going over the same content that is in the videos that I'll link, but I might be doing it a little bit faster, maybe a few less examples than what I do in that video. Or in those videos. So I'll just link those videos in case you watch this and you feel like you need a little more, you might want to check those out. But yeah, so this is going to be kind of like the last couple topics we did, where this video, we're not going to be doing any calculus. We're just going to be talking about, how this coordinate system works, kind of familiarizing ourselves with it. And then in the next video, we'll learn a couple of different formulas involving derivatives as well as integrals. Okay, so before we get into what polar coordinates are, I want to kind of think for a moment about our usual coordinate system. So the typical coordinate system we use, where we describe points using an x coordinate and a y coordinate, sometimes that's referred to as rectangular coordinates. Other times it's called Cartesian coordinates. Your book uses Cartesian, so I'll use that, but I'll also write down rectangular. So Cartesian or rectangular coordinates. Well, how do they work? Let's think about why would you label a point with an x coordinate and a y coordinate? Well, if you have some point on a plane, how can you effectively describe where that point is located? You can describe how its position basically in the horizontal direction and the vertical direction, right? If you can describe where it is positioned horizontally and where it is positioned vertically, that will be enough information to really pin down where that point is. So Cartesian or rectangular coordinates describe the location of a point and how do they describe it? They describe it by its horizontal and its vertical positions. So for example, if we have a point here and the x coordinate is x and the y coordinate is y, well, what is that referring to? X is referring to horizontally, how far do you have to go and kind of in what direction to get to this point? And then the y coordinate is saying vertically, where is this point positioned? Okay, so what would be another way to kind of refer to where a point is in space? Well, what we can do instead is we can use an angle to describe basically like the direction of where that point is. And then we just need to include another number to tell us how far to go along that angle. And so this system is going to be called polar coordinates. So polar coordinates they describe the location of a point not by its horizontal and vertical position, but by its direction. And so direction we'll see is basically kind of the angle at which it's located. And then the other thing we'll need is some idea of distance. And we'll see that distance is maybe not exactly the right word, but I think it kind of gives the right idea of what we're talking about here. So for example, let's say we have a point somewhere in our plane. So the first thing we can figure out is, what is the angle that this point lies on, right? Like where positionally, if you kind of swivel like a pencil around in a circle, you can get all these different angles, all these different directions, right? And so if we start at the positive x-axis and we measure, what is the angle that it takes to get to this point, this angle, let's call that theta. And then the other information, so just the angle alone isn't enough to tell us where to go, right? Because we have all sorts of different points that lie on this angle. So the other piece of information we need to kind of really pin down where this point is we need to know what distance this is here. And so this distance we'll refer to as r. And so what would be the polar coordinates of this point? It would be r comma theta. So the picture I just drew here is an example where r is a positive number. I also want to sketch an example where r is negative, and then we'll do some examples, some like concrete examples in a moment. But really the main idea to understand is that if the r value you're given is a positive number, that means that you're traveling basically right along the same direction where your angle is already pointing. So let's say that we have now the same exact angle of theta. So I'm just going to try to sketch something that looks about the same. So let's say that we have this angle theta. But now let's say we have a negative r. So what is that going to mean? It's going to mean that instead of traveling this way along our angle, we're actually going to kind of turn around and go backwards along the same angle, but in the opposite direction. And so what I like to do when I draw these is I'll draw an arrow to really emphasize which way is this angle actually pointing. And then if I have a negative r value, it's like, okay, it's actually going to go away from that. And so if you have a negative r value, that's going to look more like this. And so this would be the point with the coordinates negative r theta. Okay, so I want to do a few examples of actually graphing different polar coordinates. So this, by the way, this is kind of like, you can think of this as polar graph paper, because basically it gives us all of these different angles. So we have pi over 6, pi over 3, pi over 2, pi over 4 would be this angle between. And then notice that there's these concentric circles. So why is that? Well, basically, if you're trying to go a particular distance in a particular angle, using grid paper isn't going to work, right? So maybe let's actually jump into this example, and I think it will show you why we want to have the paper to look this way. So let's say that we wanted to graph the point. So we're going to graph 3 pi over 6. Oops, forgot about my color code. Pi over 6. Okay, so how would we do this? Well, even though the points are, I always kind of wish that they were listed in the other direction, because really the angle is kind of the first thing you want to look at, because that's really what kind of tells you where to go when you do the distance. So here we go to an angle of pi over 6, and so here is the angle of pi over 6. So I'll just kind of mark that down and then put an arrow, because that is, you know, where the angle is really pointing. And then how would we figure out where 3 is? Well, we need to go a distance of 3 along that angle. And so that's why it's really important that this graph paper has circles on it, because a distance of 3 along this angle is going to look pretty different than a distance of 3 along, let's say, like this angle. And so how do you kind of draw all of the points that are at the same distance, regardless of what the angle is? Well, that's a circle, right? So a distance of 3 along this angle would bring us to this point here. So we'd go distance of 3, that puts us here, and this would be our point. Before we do the next example, I just want to quickly show you in Desmos. So we'll be coming back to this because we'll be doing some graphing later on. But I just want to show you how you can actually get this setting. So if you go to the settings here, there's 2 options for grids. So this is kind of the conventional XY coordinate plane grid, and then next to it you'll find the polar grid. Unfortunately, Desmos doesn't allow you to graph points in polar coordinates. It does, as we'll see, let you do graphs, but just kind of heads up, if you're trying to like check your work of graphing a point in Desmos, it's not going to work. Okay, so let's do another example. Let's now graph. So similarly, let's graph now actually negative 3 pi over 6. Okay, so how would this work? Well, basically we start the same way we did on the other one. We start by identifying our angle and saying, okay, it's pi over 6, so that's this way. But now because our R value is negative, that tells us that we're going to go along this same angle, but we're going to go away from the direction that the arrow is pointing. So we'll go to a distance of 3, but kind of in this opposite direction. And so that will give us this point here. All right, let's do just one more. So let's graph the point 2. Actually, I'll make this a little harder. Let's do -2, comma, 7 pi over 6. Or sorry, 7 pi over 4 is what I meant to say. Okay, so this is where you have to remember your unit circle angle. So what does 7 pi over 4 look like? Well, that would be, the way that I like to think about it is just count up your pi over 4s, right? So 1 times pi over 4 would be like here, 2 times pi over 4 would be here, 3 times pi over 4, 4 times pi over 4, 5, 6, 7. So 7 times pi over 4 puts us into the fourth quadrant. And so our angle is going to be like this. And so it's pointing in this direction here. And so now our R value is -2. And so that means that we're going to go in the same angle, but we're not going to go towards the arrow. We're going to go away from it. And so that's going to put us at a distance of 2, but in this kind of opposite direction. And so our point would be here. So one thing I want to bring up that's kind of important to know and realize about polar coordinates is that unlike rectangular coordinates, there's always going to be actually infinitely many names that you could give to one given point. So for example, let's say that now we want to find another name for this point. When I say name, I basically mean, maybe actually let me say this a little more clearly, and I'm actually going to use a different color. So let's now find another point r theta, and I'm just going to use a different color here so that we can graph them both on the same thing without any kind of confusion. Let's say r theta that gives the same point when graphed. So as I said, there's actually infinitely many answers to this question, but how would we come up with one? Well, one thing you can always do is find another angle that is coterminal with the given angle. So another example would be, how could we get an angle that looks like pi over 6, but that's actually a little bit different? Well, if we went around the unit circle once and then again, so that would give us an angle of 13 pi over 6, right? 13 pi over 6 would be the angle. Let me maybe label this here. So this was pi over 6. If we go around instead like this, that's going to be 2 pi plus pi over 6. So that's 13 pi over 6. And then the R value would still be the same, right? And so an answer for this could be 13 pi over 6. Right, so basically any angle that is coterminal with pi over 6 is going to give you the same point if you leave the R value the same. Let's do something similar here, but let's actually try to come up with a point that has a positive R value. So find a point. Again, let's do R theta with, let's now try to do it with a positive R value because this one has a negative R value. And we want to give the same point that when graphed. Okay, so how would we come up with a positive R value? Well, that would basically mean that instead of having this angle, right? So this was the angle pi over 6, and that's what gave us this arrow that went this way. So if we wanted to have our point be along the positive direction of the angle, that would mean that we would want to instead have this angle, right? If we did that angle, well then the angle would actually be pointing the way we wanted. And so what is that angle? That angle is, so if we went to 180 degrees, that would be 6 pi over 6, right? And so this angle is 7 pi over 6. And so if we had 7 pi over 6 and then positive 3, that would work, right? Because 7 pi over 6 would point us in the right direction so that we could travel in that direction instead of against it. So again, there would be other possible answers that would work here, but one answer that would work would be to say positive 3, comma, 7 pi over 6. So, I mean, this isn't super duper important because usually you just need one name for a point, right, to graph it. But I just want you to be aware that there's this kind of repetition that can happen with polar coordinates, is that there can be multiple names for the same point. Okay, so the next thing I want to talk about is how do you convert between rectangular and polar coordinates? So converting between rectangular, or I guess I should say Cartesian, that's the word that your book uses. Okay, so the kind of easier conversion to do, in my opinion, is to go from polar to rectangular. So let's start with that first. So first one we're going to be looking at is going from polar to rectangular. Or sorry, I keep saying rectangular. That's because it's weird. Your calculus book and the pre-calculus book are kind of, they're like by the same author and the same publisher as well. But in the pre-calculus book, they say rectangular. In this book, they say Cartesian. So that's probably why I'm mixing the words up. Okay, so polar to Cartesian. So what does that mean? That means that we know the polar coordinates and we're trying to find the Cartesian coordinates. So let's say that we know that this point has polar coordinates of r theta. So what does that look like? That means that, again, this angle here is theta, and this distance is r. And what are we trying to find here? Well, we're trying to find x and y. And let me just be consistent with my color usage here. Let me just see real quick. Okay, so I use orange for the horizontal. So we're trying to find this distance and this distance, right? That would be the x and the y coordinates. That's what we want to find. Okay, so how do we go back and forth between, these kind of relationships between angles and sides of a triangle? Well, trigonometry, right? So for example, if we were to take sine of theta, let's say. So what would you get if you did sine of theta, looking at this triangle? You would get y over r. And similarly, if you did cosine of theta, looking at this triangle, you would get x over r. And so if we solve this, we can solve each of these for x and y, right? And so we can get y is equal to r times sine of theta. And then x is equal to r times cosine of theta. So these, I'd say, of all the stuff we're going to talk about on this page with converting between polar and Cartesian coordinates, this is probably the most important thing, is that if you're trying to, if you know what r and theta are, you can easily find what x and y are just by doing sine of the angle or cosine of the angle and then multiplying by the radius. So we'll see an example of that in a moment, but I want to first talk about how to kind of go the other way. So I'm actually just going to get rid of this one and reuse this. Okay, so now we're talking about a situation where we know the Cartesian coordinates and we're trying to find the polar coordinates. So this is going from Cartesian to polar. And so this is a little bit trickier, or it isn't really, but we'll see that the formulas are a little bit less kind of clear. And the reason for that is that basically there's multiple polar coordinates, right, for one Cartesian. Whereas if you have polar coordinates, if you have one set of polar coordinates, it only changes into one set of Cartesian. But we just saw on the other page that there's multiple names for polar coordinates that refer to the same thing. And so that's basically why this translation will probably seem like a little less, I don't know, clear. But yeah, so what's the translation? Well, let's think about how is R. So again, we're trying to go from Cartesian to polar. So let's say we know X and Y and we're trying to find R. So what's the relationship between X, Y, and R here? Well, X squared plus Y squared is going to be equal to R squared, right, by the Pythagorean theorem. And notice that, I'm not writing this as R is equal to the square root of X squared plus Y squared. You might think that would be a better way to write it. But the problem is that we're not going to assume here that R is positive, because R could be positive or negative. So that's why this is kind of left open-ended. In the way it's written, R could be positive or negative. But again, I think once we get to an actual example of this, you'll see it's really not that hard. It's more just that if we're trying to write something down in complete generality, we have to kind of leave it a little bit open-ended. Okay, so now let's think about how is theta related to X and Y. Well, what would be a trig function that directly relates theta to X and Y? Well, we could use tangent, right? So tangent of theta would be equal to the opposite side, which is Y, over the adjacent side, which is X. So again, notice I'm not saying inverse tangent of Y over X is equal to theta, and that's because we want to kind of leave it open-ended for different possibilities for theta, right? Because you can have multiple values of theta that correspond to the same point. Okay, so let's see how this actually works. Because like I said, I think, this won't be as confusing as it seems when we do an actual example. So first example we'll do is going from polar to Cartesian. So we want to convert the point 2 comma pi over 3. So 2 pi over 3, we want to convert that to Cartesian coordinates. So I'm going to draw a picture, but honestly, you could just go directly to that formula and plug it in. I just want to draw the picture so we can really kind of make sense of what we're doing. So pi over 3 would be this angle here. And then we would go a distance of 2 in that same direction. So that would land us at a point that is right here. Okay, so how would you do this? Well, we saw above that you can find the x coordinate by doing r times cosine of theta. And so in this case, x would be equal to, so r was equal to 2, right? That was this distance. So we'd have 2 times cosine of pi over 3. And so what is cosine of pi over 3? It would be 1/2, right? And so 2 times cosine of pi over 3 is going to give us 1. And then to find the y coordinate, we say y is equal to r times sine of theta. And so that would give us y is equal to 2 times sine of pi over 3. And so sine of pi over 3 is square root of 3 over 2. And so we would get 2 times square root of 3 over 2, so that is just square root of 3. And so the x and y coordinates would be 1 square root of 3. Okay, let's do one where we're going the other way now. So now we're going to convert a rectangular or Cartesian coordinates, we're going to convert it to polar. So we're going to convert the point 1, -1. to polar. So I should probably do this a little differently. Let's make this more like that. Okay, so what does the point 1, negative 1 look like? Well, it would be like here, let's say. Make it nice and big. So that means that the x coordinate is 1 and the y coordinate is negative 1. Okay, so we could go up to those formulas and we'll kind of confirm that the formulas work with our picture in a second, but I think in this case we can probably work it out just by kind of looking at the picture, right? So if we're at a point of 1, negative 1, what is this angle going to be? Well, it's going to be like a 45-degree angle, right? And we're in quadrant 4. So what is this angle going to be specifically? Well, there's actually different names we could give to it, right? But one angle we could call it negative pi over 4. We could also call it, for example, let me think. Oh, my brain is not 7 pi over 4, right? We already did that one earlier. So 7 pi over 4 would be coterminal. That would be if we measured it this way. So either one would work as our name for our angle. And then what would the distance r be? Well, basically you can just kind of use the Pythagorean theorem here, right? And that's essentially all that's going on in this formula, right? It says x squared plus y squared is equal to r squared. And so if we take 1 squared plus negative 1 squared is equal to r squared, that's going to tell us, so on the left-hand side, we're going to get 2, right? We'll have 1 plus 1, so we have 2 is equal to r squared. And so that tells us that r is going to be equal to plus or minus square root of 2. And so how do we pick which one it is? Well, in this case, we've already drawn our angle, right? And so we want to go in that same direction as this angle. And so we're going to choose the positive one. Whereas we could have used the negative one, right? But that would have been if we made our angle this way. So a different name for this angle could have been, that would be, I guess, 3 pi over 4. And then we could say negative square root of 2. So that's why the formulas are left kind of open-ended. It's because there's always more than one way to name your angle. But I think in this case, probably the simplest name that we can give to this angle is we can call it positive square root of 2. And then the angle being negative pi over 4. Okay, so the next thing I want to do in this video is basically get into graphing things in polar coordinates. So the way that graphing in polar coordinates works is a lot like graphing in Cartesian coordinates. Basically, you are going to be graphing points, and we can do that by making a table. And the only difference is that instead of our equations giving us a relationship between x and y, they're now going to give us a relationship between r and theta. So for example, let's say that we wanted to graph the function that we'll call r is equal to, let me see what the first example is, 2 times cosine of theta. So let's fill out this table and then plot the points and we'll see what kind of a graph that gives us. So basically all we're doing is for each of these angles, we're evaluating cosine of it, right? And then we're multiplying the result by 2. So cosine of 0 is 1, and so we multiply that by 2 and we get 2. Cosine of pi over 6 is square root of 3 over 2. We multiply that by 2 and we get square root of 3. And so because we'll be graphing this, we need to approximate that. So that's approximately 1.7. Pi over 4, we would get cosine of pi over 4 is square root of 2 over 2. We multiply by 2 and we get square root of 2. So that's approximately 1.4. Yeah, I'll just say 1.4. So I'm just going to fill the rest of these out, but hopefully you kind of get it by now. You're just evaluating cosine of the different angles and then multiplying the result by 2. And let me actually put in, so this is approximately negative 1.4, and this is approximately negative 1.7. Okay, so let's start plotting these points. So the first point is 0, 2, and so that means that we want to go to an angle of 0. So here's our angle of 0, and we're going to go a distance of 2. So here's our distance of 2. And so that's going to put our point right here. So that's our first point. The next one, we want to go to an angle of pi over 6. So here's our angle of pi over 6. And we want to go a distance of about 1.7. So I'm just going to kind of eyeball that. So 2 is this kind of circle here. 1.5 is a little bit back. So 1.7 should be like a little bit less than halfway. So I'm just going to put that point, let's say like around here. Okay, so next up we have pi over 4. And so that is going to be this angle. And we go to a distance of 1.4 approximately. And so that's going to be a little bit less than 1.5. So maybe somewhere like here. And then our next one is pi over 3. And so that one we're supposed to go a distance of 1. And so if we go to that angle of pi over 3 and go a distance of 1, that puts us right here. Then we have pi over 2. And so that is this right angle. And we're trying to go a distance of 0. And so anytime you have a distance of 0, regardless of what the angle is, that's always just going to be a point at the origin, right? Because going 0 from the origin just means you're at the origin. Okay, so next up we have, these ones get a little bit more interesting. So 2 pi over 3. So that would be this angle here in this direction. But we're going a negative distance of 1. And so that means that we're going in the opposite direction and we're going to 1, which is here. Next up, we have 3 pi over 4. So that would be this angle here. And so we go away from the arrow and we go to a distance of about 1.4. So that would be somewhere like here. And then last one we have, or sorry, 2 more. So 5 pi over 6, that would be this angle here. And instead of going towards the arrow, we're going away from the arrow to 1.7. So that's going to be approximately somewhere like here, maybe a little bit further in. I can just tell that that's not quite right. Yeah, sorry, actually, I miscalculated. It should be more like here. And then the last one that we have is pi. So that would be this angle. But we're going in the opposite direction, -2. So that puts us back at that same point we started. So the graph, if you kept plotting points, would actually start to repeat itself. And so what kind of shape do we get if we connect all these dots? Well, it's a circle. Oops. Try to do my best to make it look as circular as I can while sticking to the correct points, but it is actually a perfect circle. So this, making this table and plotting the points is fine, but there's one other thing I just want to quickly show you, and I should have left more space here, so sorry, let me just scooch this down. You can actually use that same kind of conversion that we did for converting points to convert this to a rectangular equation. And it's not going to work so well with all of them, but in this one, I think it's actually kind of nice and really shows you that this is a circle. So how would you convert this to Cartesian? Well, our original equation, right, is r is equal to 2 times cosine of theta. And so remember from the conversion page that cosine of theta times r is equal to x. And so another way of saying that would be cosine of theta would be equal to x over r, right? If we just divide both sides by r. And so all I'm going to do is replace in this equation where we have cosine of theta, I'm going to replace it with x over r. So we're going to have r is equal to 2 times x over r. So x, I'll use orange. And then here I have r. Okay, so let's multiply both sides of this equation by r. And so that will give us r squared is equal to 2 times x. So another conversion we had is that we know that r squared, sorry, wrong page here. We know that r squared is equal to x squared plus y squared. So I'm just going to go in and where I have an r squared, I'm going to replace it with an x squared plus y squared. Oops. So if we replace r squared with x squared plus y squared, we'll have x squared plus y squared is equal to 2 times x. And so let's now subtract this 2x from both sides. And so I'm going to just make everything black so that this next step I can kind of color code it in a different way. So if I subtract 2x from both sides, and I'm just going to leave a little space here and we'll see why in a second. So we can do something called completing the square here. So what we can do is, because we already have a y squared, remember that our goal is to make this look like a circle equation, right? And so circle equations look like x minus h squared plus y minus k squared is equal to r squared, right? So that's kind of our goal, is to make it look like that. And so that means that we need to be able to rewrite this part as x plus or minus something squared. And so the way we do that is this process of completing the square, which you should have learned about in your pre-calculus classes. So how would you go about completing the square here? Well, we would figure out, what's missing to make this part a perfect square, and it would be a 1, right? If we add a 1, then we'll be able to factor that as a perfect square. And so how does this thing factor now? Well, it factors as x minus 1 squared plus y squared is equal to 1. And so this is our Cartesian equation for our circle. And that makes sense, right? If we go back here and look, it's a circle with a center of 1, 0, and a radius of 1. And that's exactly what this equation is that we came up with here. So I'm not going to do this on the other examples we'll do, but I think it's just kind of nice to be aware that there is a way to convert it to a Cartesian equation, and the equation you get will still give you the exact same shape as what we found by graphing it with polar coordinates. So next I want to do another example that will initially seem kind of similar, but we'll see that the graph is actually really different. So the one I want to graph now is going to be r is equal to, so the last one was 2 times cosine of theta, right? And so this one is cosine of 2 theta. So what's the difference between these two equations? Well, in the first one, we're finding cosine of theta and then multiplying the result by 2, right? Whereas this one, we're multiplying the angle by 2 and then finding cosine of the result. So this one, we'll see that this is a slightly more complicated graph, and we're not actually going to make a table for the whole graph. We're just going to do kind of a little piece of it, and then we'll fill in the rest of it. I'll just kind of tell you what the rest of it looks like. So we're just going to look at a few kind of key angles here. So for example, if we're plugging in negative pi over 4, so what would that look like? Well, that would be taking cosine of 2 times negative pi over 4. So what's 2 times negative pi over 4? That's negative pi over 2. So what is cosine of negative pi over 2? Well, if you go to an angle of negative pi over 2, cosine of it is 0. And so for negative pi over 8, now we're finding cosine of negative pi over 8 times 2, which is cosine of negative pi over 4. And so that's going to give you square root of 2 over 2, which is approximately 0.7. Let me just scooch these over. Oops. Okay, so next we have cosine of 0, right? Because 2 times 0 is still 0, and cosine of 0 is 1. Then we have cosine of 2 times pi over 8, so that's cosine of pi over 4. So cosine of pi over 4 is also root 2 over 2, or approximately 0.7. And then finally we have cosine of pi over 4 times 2, which is pi over 2. Cosine of pi over 2 is 0. Okay, so let's plot these points. So first we go to an angle of negative pi over 4, so that's here. And then we go a distance of 0, right? So that's just a point at the origin. Next we go to an angle of negative pi over 8. So there is not a line for that, but we just want to do half of negative pi over 4, so that's going to be here. And we go a distance of about 0.7. And so that's going to put us halfway between the 0.6 and the 0.8. So that's like here. Oops, I should put it a little bit more on this angle. There we go. And I erased it, but I'll put it back in. So that was like here. Okay, so then we have an angle of 0. So that's just on the x-axis, and we're going a distance of 1. So that puts that point here. And then we have pi over 8. So again, that's going to be half of pi over 4. So that's going to be this angle here. And we're going a distance of 0.7. So again, halfway between 0.8 and 0.6. So that's there. And then our last point, our angle is pi over 4, but we're still at 0. So that just brings us back to the origin. And so how is it shaped between these points? Well, it's basically round. It's kind of like, we'll see that the overall shape of this graph is going to be like a flower. And so you can think of this as being like one flower petal. And there's like a direction to it, right? So what direction did it go? It started by going this way, and it kind of comes back this way. And so what is the next part of this? You know, we're not going to make a table for it, but I'll just kind of tell you. It basically traces out another one of these flower petals, and the next place it goes is in this direction. So it goes like this. And then it traces out another one going now this way. So like this. And then the last one it traces out is like this. So that's the graph of r is equal to cosine of 2 times theta. So I wouldn't be asking you, like on the final exam, for example, I wouldn't ask you to graph this by hand. It's a lot of work to graph this, right? But what I do want you I basically just want you to be exposed to like, what do some of these graphs of polar equations look like? And I do want you to understand the process of graphing it. So I think it would be fair for me to ask you, for example, to graph just like a little snippet of it, or to graph this one, which I think is a lot simpler to graph. But the main thing I just want you to understand is like what the relationship is between this picture and the equation, and like how you can make a table and plot points. So I want to show you in Desmos some different kind of shapes that we can get by just kind of changing these equations slightly. So right now we have r is equal to cosine of 2 theta. So that's the one that we already graphed. So it looks like what we graphed, right? So what if we did sine of 2 theta instead? Well, basically we would get a graph that looks really similar. The only difference is that it's been rotated. And I don't really want to get into this in this video, but basically that just boils down to the relationship between cosine and sine, and how you can shift one of the graphs into the other one. Because really, if you get this graph by rotating it, that means that you're just changing the angles slightly and getting the same outputs. So the difference between cosine and sine is, again, just that they're kind of rotated compared to one another. So what would happen if we go and change the number here, that's 2, if we change it to something else? So let's look at what happens if we change it to 3. So if we change that number to 3, now our graph, instead of having 4 petals, it actually is 3. And let's change it again. Let's change it to 4 this time. So we did 2, we did 3, we did 4. So when we change it to 4, now we have 8 petals. And so the general rule, and this isn't something I'm going to ask you to like memorize or anything, but it's just kind of interesting to notice, is that if you have an even coefficient of theta, you're going to get twice as many petals as the coefficient. So 4 here gives us 8 petals. Whereas if you have an odd number, so for example, let me change this back to 5, let's say an odd number, well, then the number of petals is actually going to be equal to the coefficient. So when it's even, it's twice as many petals. When it's odd, it's the same number of petals as the coefficient. So here I also pulled up, if you just type in r is equal to cosine of c times theta, that allows you to kind of change c to different values. So right now I have it set on 3, but I just want to show you that if you make this coefficient c equal to a number that's not an integer, you can actually get some really interesting looking graphs. So like, for example, this would be c is equal to 3.3. And here we have 4.1, and just kind of scrolling through these, we can see there's lots of different variations that you're getting using these different coefficients. So I'd really encourage you, like I said, we just don't have time in this class to really delve deeply into this, but I would encourage you to go on Desmos and play around with these, because I think that they can produce some really interesting graphs, the same way that parametric equations can as well. Okay, so I just want to look at 2 more really quick examples. So these ones we're not even going to make tables for, because they're pretty simple. But so far the equations that we've graphed have been ones where the equation expresses a relationship between r and theta, right? But with Cartesian equations, some equations express a relationship between x and y. So things like, x squared plus y squared is equal to 9, or 2x minus 5 is equal to y, right? Those are relationships between x and y. But you can also have equations that are just like y is equal to 2, right? So that would be like a vertical line at a height of 2. Or you could have x is equal to -3, and that would be, or sorry, I said vertical when I meant horizontal. Let me go rewind. So when y is equal to 2, that would be a horizontal line at a height of 2, right? And when x is equal to -3, that would be a vertical line at an x value of -3. So just like how with Cartesian coordinates, you can have equations like that only contain one of the variables, we can do the same thing with r and theta. So let's say that we wanted to graph the equation r is equal to 3. So let's think about what this equation is telling us. So there's no theta in this equation, right? And so what does it mean when there's no theta? Well, that means that theta is allowed to be anything. So theta can be anything. You could make a table with all sorts of different values of theta. And so as theta kind of varies and can be anything, what happens to the radius? Well, r is always 3. So what is that shape going to look like? Well, if we go to any angle we want and we're always at a distance of 3, that's going to give us a circle with a radius of 3. Because no matter what angle we're at, we're always at a distance of 3. Okay, what if we now kind of do the opposite thing? And let's say that we wanted to pick a particular value for theta and write an equation that only has theta and no r. So let's say theta is equal to pi over 3. What would this look like? So this tells us, again, because there's no r in this equation, r can be anything. But theta is always pi over 3. So what's that going to look like? Well, that basically means that we can go to an angle of pi over 3, right? So let's go to this angle. And we can put a point at every single distance along this angle. And then we can also put points in the opposite direction, right? So if r can be anything, r could be positive or negative. And so that means that we can have points basically all along this entire angle in either direction, and that just gives us a line. So this would be a line at an angle of pi over 3. All right, so that's it for this video. In the next video, we'll be getting into some calculus with polar equations. I'm going to keep it really simple. I know that it's the end of the quarter and it probably feels like there's a lot of topics being kind of crammed in. That's just kind of the nature of Calculus 2 and especially the end of Calculus 2. But I'm going to really kind of keep it simple and just focus on a couple of simple examples of how we can do derivatives and integrals both with polar equations. So I'll see you in the next video.